In this video we're going to look at how we can take any normal distribution and how we can transform the problem that we're looking at into one in terms of Z, which is the standard form, so that we're then able to use tables to calculate our required probabilities. So here we're told that we have a distribution x, and the fact that we write it then here with an n tells us a normal distribution with a mean of 25 and a variance of 3 squared. Now we often write it as 3 squared rather than 9 here, because then the 3 relates to the standard deviation, which is what we need. Now if we think about what the Z values that we use in the standard form are, it tells us how many standard deviations away from the mean the value we're considering is. So here we need to work out that Z value. So I'm going to do my number 32 here. I'm going to subtract it from 25, which is the mean, and divide it by 3, which is the standard deviation. So this is going to tell me how many standard deviations away from the mean 32 is for this distribution. So 32 subtract 25 over 3 gives me 2.33, and I'm going to do this to 2 decimal places because that's the accuracy I have in my tables for the normal distribution. So what I'm going to do now is I'm just going to rewrite this using the notation that we want. So now I'm saying that when I have a value of 32, that's equivalent to finding the probability that Z is less than 2.33. Because what I've done here is I've transformed it from a problem in X to a problem in Z. Now 2.33 I should be able to look up in my table, and I look here and I think, well actually no, I can't. I've got 2.32 and I've got 2.34. So it's going to be somewhere between these two. Now it was 2.33 recurring, so that's actually slightly closer to 2.34. So I think I'm going to use that value, so it's 0.9904. And there's a little bit of a leeway here in the exam, because if you don't have an exact value, usually they allow one either side if it's equidistant like that. But if you've got a graphical calculator, then you'll be able to calculate an exact value, which might be useful as well. So here, given a similar situation, we've got to work it out. So this time I'm going to do 35 subtract 40 over 8. That gives me negative 0.625, which I'm just going to write as negative 0.63 to 2 decimal places. And so what I'm looking for now is the probability that Z is less than negative 0.63. Now for this one I'm just going to use a sketch, simply because this one is not one I can look directly up in the table. So Z is negative 0.63. It's less than that, so it's this kind of part of the graph I'm looking for. So by symmetry I can say, well, this one over here is 0.63, must be greater than that. I can't look that up, but I can look up this white area. So the white area is the probability that Z is less than 0.63. I can look that up in the table and I get 0.7357. So the probability that I actually required, which in terms of Z is less than negative 0.63, is 1 subtract that, which is then 0.2643. And then my final question here, given this information, find A such that the probability that X is greater than A equals 0.01. So I can't use my formula for finding a z value, because I don't actually have a given number. This is what I want to work out. But the probability that x is greater than a is equal to 0.01 is going to be the probability that z is greater than, and usually use a little z here, is 0.01, and little z, therefore, I can work out, because I can use this table when it's 0.01, so the probability that exceeds 0.01 is 2.3263. So now I can use my transformation formula, because I know x, whatever that value is. When I then subtract the mean of 30 and I divide it by the standard deviation of 5, I end up with 2.3263, and therefore that x is equal to 2.3263 multiplied by 5 added to 30. Which gives me then an answer of 41.6315, and I may decide just to give that to, say, 2 decimal places again, but I'll keep that here just in case my accuracy required is a bit greater than that.